Hi students, welcome back. Today we are going to look at rotting oranges problem on LeetCode. So let's look at the problem statement first. The problem statement says you are given a m by n grid where each cell can have one of the three values. So in a m by n matrix, each cell can contain either 0 representing there is nothing in that cell, or 1 representing there is a fresh orange, or a 2 representing there is a rotten orange. Okay. Every minute, any fresh orange that is four directionally adjacent to the rotten orange becomes rotten. So every minute or in every level or cycle, any orange, any fresh oranges which are neighbors of a rotten orange becomes rotten. Okay. So basically, it's spreading the rottenness to its neighbors. We have to return the minimum number of minutes that must elapse until no cell has a fresh orange. So number of minutes required, minimum number of minutes required to for all the oranges to go bad is what we have to return. So he is telling minute here, but it's actually the number of turns that are required. Okay. And if this is not possible, we have to return -1. That means how many ever turns it takes. If some of the oranges will never get rotten, then we have to return -1. Okay. Let's look at some of the examples. Okay. In this, the given grid is 2, 1, 1. Okay. 2, 1, 1, 1, 1, 0, 0, 1, 1. In this case, as depicted in the picture, in the first minute, the first one is rotten. Okay. In the next minute, it spreads to its neighbors, which is these two. So these two are rotten. Then these two are also rotten. Then its neighbor, this one. Then its neighbor, this one. So in total, it takes 4 turns to complete. Now, if we are given 2, 1, 1, 0, 1, 1 and 1, 0, 1. Okay. So let's see how that looks like. Okay. So this is the given input. So in the first turn, there is only one rotten orange. So we'll start from here. All its neighbors will become rotten, right? So these become rotten in first turn. Level is 1. Okay, in the next level, neighbors of these things, which is this and this one, they become rotten. Okay, in the second term. Now, its neighbors. There are no oranges in any of these neighbors. These are all empty cells. Okay, so nothing can become rotten at this point. We have parsed the entire array. But if you actually look at it, there is one orange which is remaining. This is surrounded by empty spaces and hence no one can reach it. This orange will always remain not rotten. Okay, so in this case, our answer is -1. Rest of the oranges will get rotten in two levels, but even after parsing everything, one orange will remain, and that's why we have to return -1. Okay, let's look at another example. Let's say we are given these this matrix or grid. Okay, so initially when we start, we will start from the place where rotten oranges are. So if you go through the algorithm step by step, right, you can clearly see that this is a level order traversal or a BFS. Okay. So what we are doing is traversing level by level in a graph, but our starting point is multiple starting points. It's not just one. Wherever there are rotten oranges, all those points are our starting points. In this example, this one is our starting point, this one is our starting point. So we are starting at these 2 points and initially our level is 0. Okay. Now we what do we have to do? We have to find all the neighbors, which is this guy, and to this cell the neighbors are these three. Okay. What will happen to the neighbors? They become rotten. So we update them to 2. Okay. Okay. This completes one level of traversal for us. So we increment the level. Okay. Now we have to go to the neighbors of these open cells. So neighbors of this one, There are no oranges neighbors of this. This one. This is the neighbor. For this guy, this is the neighbor. For this guy, this one. For this guy, this one and this one. And we have to update all the neighbors to rotten oranges. Okay. Now the neighbors processing is complete. And we have to increment the level. So in two levels, we have covered the entire graph. Now for these guys, for the current items, there are no neighbors which are oranges. Okay, so there is nowhere we can go to for the next level, which is why we will end it. So our level is at 2. Okay, but if you observe the graph, we have one orange which is not rotten, which is why our answer would be -1 in this case. This guy is surrounded by all empty spaces and hence he can't get rotten. What if this is 0 instead of 1? Okay, then the answer would be 2. If this is 2, then also the answer would be 2. Okay, this is, since this is 1, that is why our answer is -1, otherwise it would be 2. Okay, so our algorithm is simple. We will do a level order traversal and slowly find the levels. At the end, we will see if there are any good oranges remaining. If they are remaining, then that means though we traverse the graph fully, they are still remaining. So it is not possible for them to get rotten. Okay. So that is our logic. Now let's try to write code for that. So initially, like we said, it is a BFS. So we will need a queue to store the current nodes. Okay. Let's create a queue. Linked list implements queue. And what will be there in this queue? Starting point would be all the bad oranges, right? So we will traverse this grid, figure out all the bad oranges, and we will add them to the queue. Okay. So we are going from I equal to 0, grid dot length, j equal to 0, grid of 0 dot length. Okay. And if any cell is 2, that means that is our starting point. We add it to the queue. Okay. Now to start with itself, if there are no good oranges, we can directly return, right? There is no point processing itself. So maybe it will help us if we keep track of the number of good oranges. Let's try to do that as well. So what is the count of good oranges? If there is anyone with value 1, that is good oranges. So at this point, if good oranges is 0, that means we traversed the graph or the matrix and we found out the number of good oranges. If there are no good oranges to start with, we can just return 0. Okay. All right. Now there are good oranges. There can be bad oranges. We have to do the level order traversal now. To start with, let's take the level as -1. Okay. Because our first step is not needed. That is why we are not counted. That is why we are starting with -1. Okay. Because first step oranges are already rotten. Okay. So while queue is empty, while queue is not empty, if the queue is not empty, what will we do? We will do level plus plus. Okay. And we will get the children here. Okay. What are the current children of this thing that we have to process? Number of nodes we have to process, that is queue dot size. Okay. That is the current nodes that we have to process in this level. So this level has how many nodes are there in this queue? That size of nodes. Okay. So we have to process each of this child. Okay. And how do we get the child? We have to get it from the queue. Okay. So our queue definition has integer array. Correct. That means it has two coordinates, 0 and 1. 0 is x, or rows and columns basically. Okay. That represents a cell. We remove the item from the cell. So we are removing a child from the cell, and for each of it, we will find the neighbor. Okay. For each cell, we have to find the neighbors. Let's say we have a method to get the neighbors. Okay. I'm saying I will get neighbors of this cell Okay, and I will add them to the queue. Neighbor of this cell is nothing but the thing that we have to process in the next row. Correct? So I'll add them to the queue. Okay. What happens to the current cell? The current cell is bad because we are currently processing that cell. So we set it to 2. Okay. We add the neighbors to the queue, update the current cell to the 2, and we were also keeping track of number of good oranges, right? So here at this point, one good orange became bad. So let's keep a track of that count as well. Okay. So far what we did, while queue is not empty, we got all the nodes in the queue, and for each node, we got all of its neighbors. We added the neighbors to the queue and we updated the current node's value to 2, which is updating it to rotten. Okay. So that should help us process the entire graph level by level. Okay. And at the end, we will have number of levels in this level variable. But there is also one catch. If any good orange is not accessible, then we have to return -1. That means a good orange was surrounded by empty spaces. How do we find that case? So we were decrementing the number of oranges that are getting rotten, right? And we have the total number of oranges. So after we process the graph, if there are still any good oranges left, then that means we have to return -1. Otherwise, we just return the level. Okay. So that is simple. Now the missing piece here is how do we get the neighbors of a cell? Okay. So getting the neighbors of a cell is very easy. We have done this before also. So I will just copy paste the code and walk through you. Okay. So we have a grid and we have a starting point and we need all the neighbors. We need 4 directional neighbors. So I'm taking this directional array and for each of this direction, I'm calculating the adjacent row and adjacent column. So the probable neighbor. Okay. If the probable neighbor is within the reach of the matrix or within the dimensions of the grid and if it is a orange, then I am adding it to the neighbors. Okay. So if it is a valid cell in the matrix and if it is a good orange, that's when we are calling it a neighbor. Okay. That is what we are doing it here. So we have another small function here which is checking for the boundary conditions. So it is just checking for the row and column count here. Okay. So that is all we have. So initially we found all the bad oranges and we added them to a queue. Or we also found the count of good oranges. If good oranges is 0, we simply return 0. Otherwise, we do a level order traversal starting from all the bad oranges, which is nothing but all the elements in the queue. Okay. How do we do level order traversal? We empty the queue on each level, get all its neighbors, add it to the queue, and the current node we update it to 2. That's what we do. How do we find the neighbors? Neighbors is nothing but any cell which is on the 4 directions north, east, south, west of the current cell, which is inside the matrix and which has a good orange. That is what we call a valid neighbor. Okay. Okay, then let's submit this and see. Okay. Okay. So it worked fine. So what will be the time complexity of this one? We are traversing the matrix once to find out the bad oranges and then again to traverse the graph. It's in total 2 times we are doing n by m traversal, but it's 2 is constant, so it's order of nm. Okay. Yeah. That's all we have for this problem. Thank you for watching.